Well, what we have is a bunch of observations that we made with our experiment. You can see them here plotted as the blue points. And what we'd like to do is to somehow discover the most likely line that represents the theory that we hypothesize that explains how the spring works, given the observations that we have. So what we did is that we have for a particular force that's being applied, we have the notion of adjusting the parameters of our prediction to come up with a particular prediction. And what we'd like to do is to adjust those parameters so that the prediction is the most likely one given the observation that we made. And we discovered that the difference between the two of those observations and the prediction we described as the error. So the likelihood that the prediction is the right one is sort of determined by the size of the error. So we take the ith observation and we compute the error by subtracting off the ith prediction. And so this is the likelihood here of such an error occurring. And the likelihood gets bigger the smaller the error is. And we saw that on the previous slide, that small errors are much more likely than large errors. And what we'd like to do is to now say, okay, well, I have many such observations that I've made, and the likelihood of making all those observations will be, like with probabilities, the product of all the individual likelihoods. So if I'm going to go off and look at the likelihood of each observation, what I'm going to do is to then multiply all those together. And here's what my job is going to be. I want to choose the parameters, okay, the parameters of my prediction. So in this case, it would be the constant 1 over k. That's the slope of the line. I want to choose the slope and then the intercept of the line such that that particular choice of parameters maximizes the likelihood. So I want to maximize this product. So we want to maximize the product of the likelihoods of the errors. So that will actually be the same as minimizing 1 over the product. So if we want to minimize this product of the likelihood of the error, so 1 over the product. So let's work on that a little bit. Let's actually start by taking the log. It turns out that whatever parameters will minimize the 1 over the product will also minimize the log of that expression. So let's take the natural log ln. And so the natural log of 1 over this product of, well, let's see. So the natural log of 1 over something is minus the natural log of the product, and the log of the product is the sum of the logs. So we basically will do the same summation here, and now what we want is the natural log of this error, and I'll write it out this time. Observations minus the predictions. Okay, so the likelihood of the error. So we're still trying to minimize this. That's our goal. And now what we're going to do is take advantage of our knowledge about what this error, the likelihood, looks like. So we're going to use our knowledge to expand this further on the next slide. So just carrying on from the previous slide, we're going to want to minimize this sum, which is the natural log. And now I'm going to go off and write in the likelihoods of the error. So it's 1 over 2 pi sigma squared. And I'm just using the formula here for the normal distribution. So this will be E, and this will be minus, and now the error itself here was the observed value minus the predicted value squared all over the variance of the errors. Okay, so that seems pretty straightforward. Let's go ahead and simplify that. So we were I'm going to take care of the minus sign here as I do the simplification. So let's see. So the natural log of a product is the same as the sum of the natural logs. So, and the natural log of 1 over something is minus the natural log of the something. So we'll use that minus to cancel out some of this. So this will be the same as the natural log of the square root of 2 pi sigma squared. Okay, plus, and now minus of the, I'm going to move this minus sign again in, minus of the natural log of this guy, which this is the natural log of e to the something is something. I'm going to take care of that minus sign, and so this will be observation minus the prediction squared all over sigma squared. Okay, and we're going to be wanting to sum all those up. So this is the same sum as before, and we've just used the minus sign and expanded out the log a little bit. Now let's observe that some of these terms are constant. This is a constant, as is this guy. He doesn't change. Presumably the error processes are sort of stable and their statistics are stable as we're making our measurements. And so what we discover is that this guy here, particularly if we're doing a minimization problem, this is all proportional, and I can just get rid of the constants. They won't affect the minimization at all. The same choices for the parameters of the prediction that minimize this equation will also minimize this equation. So I'm just taking out all the constants. We don't need them here to help us with our minimization problem. And I end up with that, which is sort of a magic result in the business of processing data points. And this is what's called the sum of the square of the errors. Okay, or SSE for short, sum of the square of the errors. And if we minimize that, then we'll have made the most likely choice of the parameters. If we choose parameters such that we minimize the sort of the sum of the square of the observed errors, then that will be the most likely predictor for the observations that we have. And we actually have sort of a nickname for this guy, as we often call this as sort of a shorthand, the least squares. Finding the values of the parameters for the prediction that minimize the sum of the square of the errors is a very common thing to want to do to data points. And in fact, PyLab has a built-in procedure that will do that for us. It's called polyfit. Let me show you how to use it. So the first example here is finding the parameters for a linear predictor. So we're making the assumption that the prediction, in this case of the extension of the spring, is based on a linear relationship between the mass and the observation that we make. So we're asking polyfit to find us the parameters A and B. So it's going to find us those, given, in our case, a bunch of forces that we applied to the spring and a bunch of observations that we made. And its job is to find the best such set of parameters that minimizes the sum of the square of the errors. We can also ask for fits with higher degree polynomials. Here's one that does a parabolic fit, so this would be a second degree equation. Here we're assuming that the relationship between the prediction and the observation or the basic parameters and the observation is governed by a second order equation. So ax squared plus bx plus c. So given again the forces that we've applied and the observations we made of the extensions, we could get a second order fit. And in fact, if we set this parameter to 3, we would be fitting a cubic equation, so forth and so on. So our next step is to actually use these routines and try to find those parameters given the observations that we made.